Hello, can you hear me?
Yep.
Okay, let's start. Um, Good morning, everyone. Okay, so I'm going to start. So we were doing directivity in the last lecture, and I have posted homework on Canvas. I will discuss this homework on next Thursday. Uh, and it's the next Thursday because by then, yes, next Thursday, by then you all will be able to see and try to solve this homework. Okay. So then we will discuss this homework and we will be able to uh, solve the remaining questions which you will not be able to do it. Okay. Other than that, I think 25th we can have the midterm. Is it fine? So because I think
What week did you say?
25th,
Okay.
okay. So I think 25th will be good for us. So we will be having midterm or 25th. Um, so there will be another homework that I will be posting. So maybe um, um, I before the midterm, I will post the solutions for both of them so that you will be able to look at them. Okay. Okay. So let's start. So we were doing directivity, and just this time we will uh, talk about the same directivity and we will do a little bit more general expression of it. So so a more general expression of directivity includes, so previously when we were talking, we were just including the radiation pattern with theta variance. So now in the general expression, we will include both variants like the theta and phi. Can be developed to include sources with radiation pattern that are functions of theta and phi. So we can also write this as like the radiation intensity of those sources as function of theta and phi. That could become we said that this would be what you should say, e over 2 eta square. So e can be in the direction of theta and phi. So when we will define its maximum quantity, that would be, we need to define maximum quantity because we do direct maximum directivity when your radiation intensity is maximum. Okay. And another thing, we know that our PRAD is equal to okay. So when we will define directivity, it will be divided by PRAD. So I'm just replacing PRAD here as well. So this is directivity, that's the general expression of directivity, which includes both theta and phi. But if we talk about maximum directivity, that would be equal to the same PRAD here. 0 to 2 pi, 0 to pi. I just do not want to move it too much. Okay. F theta phi sine theta d theta d phi. Okay. So now if you move this quantity down, this will become 4 pi, 0 to pi, 0 to 2 pi, F theta phi by F theta phi max d solid angle. And this quantity, F theta phi max, and this quantity will be the normal, like the normal component, because you are dividing it with its maximum amplitude. And we can also define it. So you all have written it, or can I move? So I think someone mentioned it that I am still writing fast. So I'm just sorry. I am trying my best to be with good pace, okay? So let me know when you are done. Do you have any questions? Louis, are we good? We can move forward?
Yes, thank you.
Okay. So okay, so what I'm saying was that we can write this thing as this is the normal, and here n means that this is the normal component d theta d phi. Okay, and uh, then our maximum directivity will be 4 pi over the beam solid angle A, which incorporates in it the normal component of radiation intensity. So we can also define this beam solid angle as is defined as the solid angle through which all the power of antenna would flow if its radiation intensity U is constant for all angles within this solid angle. So this particular solid angle we are defining in which the radiation intensity is constant or normalizes. So it's also a kind of normalized solid angle, beam solid angle. So what we actually doing is previously what we have done is we were calculating radiation intensity and radiation density. But now the difference is that we are introducing another quantity that is directivity, and we are defining all of our old parameters with respect to directivity. So it's just the mathematical version of it, but it has a meaning in it. That's why we are defining it. So now I will come to the approximate directivity, okay? So we learned about two types of parameters till now, radiation patterns till now. One radiation pattern is that is omnidirectional radiation pattern, right? And the other radiation pattern is that is uh, like the one lobe radiation pattern, unidirectional radiation pattern. So we will, these two types of the radiation patterns are, which are the most common types. Okay, so that's why we want to approximate our directivity on these types. So approximation means that we do not want to solve it in the exact manner, but we define and approximate formulas to calculate the directivities. So Okay. So what I'm saying is that we have two types of patterns. Okay. Uh, First pattern is, so that is directional or pattern, and this is omnidirectional pattern. Okay, so the directional pattern is that in which you have a lobe like this in the direction of Z, and there could be minor lobes here, right? So this is your directional pattern in which there is one major lobe and the small minor lobes, okay? So in this type of pattern, if we want to approximate our directivity, we need to little bit define, we need to see what we are doing, okay? So if I just do this, so I will say that if this is the beam solid angle I'm seeing from the top, then it can be composed of these two types of beam widths, okay? So I will also define this, that what is this, the angular separation, which is perpendicular to each other. So let's say this angular separation is theta 1r, and this angular separation is theta 2r. So if the two angular separations, theta 1r is not equals to theta 2r, where r is the radian, or this theta means that we are considering the beam widths, then this is non-symmetrical pattern. And if they both are equal, then this is symmetrical pattern. So we are saying, so the first approximation is saying, so this is this first approximation of directional pattern. That your beam solid angle is equal to, or approximately equal to, the multiple of two beam widths, which exist in the perpendicular plane. So what we are saying is that the beam solid angle is approximately equal to the product of half power beam widths in two perpendicular plane. So what it means that we are approximating it with the multiple of two beam widths instead of defining it as sine theta, d phi, 0 to pi, and 0 to 2 pi integral. Okay? Is it clear? Okay.
I'm sorry. Where's theta 2 again? Like the one that's
Okay.
perpendicular to the top?
So if you have a circle, like if you have this beam, okay, 1 minute. Maybe I should make it a little bit more bigger. 1 minute. So if this is my lobe, okay, and this is my solid angle, I'm thinking. So this is my first half power beam width, right? So this I can write as theta 1r, okay? Yes, and the other will be in the perpendicular plane. So the other will be so this is at the back, so I'm not, or I can just go with it. So this would be your second theta in the perpendicular plane. Got it? I mean, if you see a solid angle that is projected, it is supported by two perpendicular planes, okay? We will, I think, get more clarity in onwards, but these two perpendicular planes, whatever angle they are making, if it is, they both are equal, then it is the symmetrical pattern. So it's kind of thinking that if you are looking from here, the beam solid angles horizontal, if this is, I mean, circular, so it's not pretty much horizontal, but it's looking from here, like the front and the perpendicular direction. So the half power beam width from front or in the perpendicular direction, the half power beam width. Both should be equal for the symmetrical pattern, and for non-symmetrical pattern, they are not equal. Is it clear?
Yeah, that made sense. Thank you.
Okay, so that's what we were saying, that this is our first approximation, okay? So I will go with this. So due to our first approximation, I can write my directivity as theta 1r and theta 2r. So I think they are using some other symbol, so I will also use it. So this is the symbol they are using for that. They both are same thing. So this is 4 pi divided by the multiple of the like the half power beam widths in the perpendicular direction. So this approximation is called cross equation. Okay. Okay. And then you have all sorts of things that like you can define that this is your half power beam width in one plane, and this is half power beam width in perpendicular plane. Okay, and if you want to define it in degrees, it will be, so because this is in the radians, so in degrees, you just have to multiply 180 by pi squared. And this will become, not here, 1D and 2D. Okay. So this is your maximum directivity. This is the first approximation. Okay. Sounds good. So I mean, when you multiply this, it will come as 41,253 by 1D, 2D, right? And if you want to see this, but with time, they did another approximation for arrays. They said that for planar arrays, so planar arrays are the 2D arrays, which are having elements in the X direction and elements in the Y direction. We will talk about it, but you just need to say that for planar arrays, they a little bit change this approximation, that this is 3240, like the first numerator is a little bit different. Okay. So that is the first approximation we talked about in case of directional pattern. Okay, so we are good about this. This is our first approximation. And in this approximation, you are thinking that you have one major lobe and very low intensity minor lobes. So that's what I made it here, I think, that there, if there are minor lobes, they should be very, very low intensity. Okay. Okay, so now the second approximation of the same directional pattern, if we talk about. So another approximation, or the second approximation, says okay, so the second approximation said that, and this is Thai and what? Pereira equation or approximation, you can say. Based on their equation. Okay, so the second approximation said that the directivity is actually, the expression of directivity is actually equals to the mean of two directivities, or the arithmetic mean, that's what they're saying, where the other two directivities are based on the half power beam within E and H plane. Okay, so where D1 is, so these are, yes, someone has question, Jonathan?
I don't have a question.
Oh, okay. So I'm saying that it's just, approximations. So that's why we are not going into details how they come from. We will just use them to compare it with our exact directivity, that whether we are able to get, like whether these approximations are good approximations or bad approximations. So that's why. sine theta d theta, and this is equal to 16 ln 2 by 2r squared. Okay. So these are two directivities where you're in half power beamwidth in E plane plane. Okay. So that's I mean, you can find the values from your book too. So for the both directivities, and this is equal to 22,181 22.181, and this is equal to 1r squared plus 2r squared. So when I write r, I mean half power beamwidth in radian. When I write d, they mean half power beamwidth in degrees. So this degrees, they are okay. Do we have any question? We are good. Can we move forward? Are we good?
Yeah.
Okay. Okay. So we define two types of approximations in directional pattern. Okay. So we will come back to that approximation. Or let's discuss first this one. Okay. So I will discuss this approximation. I have to share my screen. Just a minute. So if you see this thing here, can you see this? Slides?
Yeah, we see it.
Okay, so in this way, you know that we have defined two types of approximation here. Okay, 1 minute. I will not go through this first. So another thing I want to describe is, so there are three equations now we have, right? The first equation is the exact equation for the beam solid angle. The second equation is the cross equation, and third equation is Thai and Pereira equation, right? So these are three types of approximations we have. Now we will compare them, but we can also see another thing. 1 minute. So the type of pattern that we are discussing here is the pattern with the one major lobe. Okay, So they said that this type of pattern is actually the pattern which can be shown, the radiation intensity can be shown as the different powers of cos theta. So if in the radiation intensity there is cos theta, you will see a major lobe going upwards. Okay, so let me show you the previous things that we have done. So this is the type of pattern in which your radiation intensity is cos 4 theta. I will move further back. This is the radiation pattern that is in the figure 2.15 in your book. Okay, we will come back to that, but I'm just showing that how the radiation intensities can be generalized. So if you have cos or multiple of cos theta, this will be your radiation pattern, most likely, okay? I will move further back. So this is your slides for chapter 2, but I will move. So this was not the major lobe thing, right? So this is not cos theta. This is the sine theta thing. In this case, your radiation intensity was sine theta. Okay, so in other words, what I'm trying to say that if you have one major lobe directed towards the z direction, its radiation intensity is in terms of cos theta. If you have a lobe which is omnidirectional, its radiation intensity will be in terms of sine theta. Okay, let me move a little bit further back to, let's just compare our further things. So let's see this thing. This is also cos theta. Okay. And I don't know whether we have further or not, but that's what I think the difference between omnidirectional pattern and the directional pattern is the radiation intensities. Okay. Okay, sorry. We were where? Arithmetic mean, here. So I was here. So this is what I'm trying to say, that in this time, you have this pattern for the unidirectional pattern, and the n can vary, like this pattern can vary multiple times. Another thing with this n is that as the n varies, as the n getting greater, you are seeing more narrow band. So means in terms of arrays where your beam width is very, very directional, your this quantity should be larger. Okay. Am I clear about this? Okay. So what I was saying is, now they have compared the cross equation and Thai and Pereira equation for different n's. So it means that as the n getting larger, as n getting larger, you will have more narrow beams, means there in the array, there are more number of elements. So if you see in this table, so this is the values they are getting from exact equation of the directivities. And these are the values, what I should say, these are the values from the cross equation. This is the percentage difference. This is the values from Thai and Pereira's equation, and this is the percentage difference. So what they say, they say that cross equation is more accurate in the less n scenario, where you have maybe less number of elements in arrays, okay? As compared to Thai and Pereira's equation. But Thai and Pereira's equation is more accurate for large number of n's, okay? Or maybe when you're dealing with more big arrays. So to compare this scenario, they made this graph in which this says that as you move your n, as your move n is higher, your half power beam width is getting lower. because it makes more directive. And these are the comparison patterns. So for very, very low ends, you are near to cross, but for high ends, you are near to Thai and Perez equation. Most of the time, your Thai and Perez equation is more accurate. Is it clear? You get more confused? Eric, what do you think? Good. Sarah?
Good.
Good. Andrew?
Yeah, I follow.
Okay. So one more thing I want to show you. Okay. It just may be a very, very raw thing, but I just tried last time for you, so I can just show you. Maybe I have it here. Yes, I have it. 1 minute. Or maybe after the lecture, I will show you. Once the lecture will stop, I will show you. Okay. So now we are done with the one of the approximation. Okay. Now I have to do the screen. Okay, so we said that these approximations are for the radiation intensity theta 0, 0, 2. Another thing you will note that for the directional patterns, you always lie in the above, like the pi by 2, the plane which is greater than pi by 2 for the theta plane. Okay. So this is the general like the intensity we are working on. Now we come back to the omnidirectional patterns. Okay, so now we are getting ourselves compared here in the omnidirectional pattern. So in omnidirectional pattern, we are talking about the patterns which are somewhat like this. I don't know how to make this, but it's kind of this. And so it's kind of this kind of. I mean to say, you know what I'm saying. So this is the omnidirectional pattern. Maybe I should draw this. So this is your pattern, and there may be some lobes here and in the bottom, but this is the donut shape pattern you have. Okay, so in this omnidirectional pattern, your radiation intensities are somewhat like this. But in this case, what should be your value of theta here, like the range?
Is it pi?
Is it pi? Yes, it is pi. That's right. Okay. Okay, so we will move towards the approximation. So the first approximation of this omnidirectional pattern is called McDonald's approximation. Okay, so the first approximation is McDonald's approximation. Okay, so McDonald's approximation says that if you have omnidirectional pattern with little bit of minor lobes, then your directivity is minus 0.0027 half power beam width in degrees square. Yes. So this is the McDonald's approximation. Okay. So then your like the directivity is 101 divided by half power beam width in degrees minus 0.00027 half power beam width in degrees. The second approximation we have is the Poisson approximation. But in the Poisson approximation, the difference between both approximation is that the first approximation is more accurate with minor lobes, but the second approximation is more accurate with minor lobes of very, very low intensity. So it's more towards the ideal scenario, the second approximation. And that is Poisson's approximation. So in Poisson approximation, our directivity is minus 172.4 plus 191.818 plus 1 over half power beam width in degrees. So in exam, if I am asking you these things, I will give these formulas, okay? Like if I'm asking you to compare your exact beam solid angle, like exact directivity with approximate directivity, so I will give you these formulas. Okay. So these are, yes. So these are our approximations. I'll show you one more thing. Are we good with the writing? Okay. Okay, so let me share my screen then. We will see another thing in the omnidirectional pattern. Okay, so these were the approximations we saw in the directional pattern. For omnidirectional pattern, we can see that this is our radiation intensity in terms of sign. Then if we move, with this is with the minor lobes, and this is without minor lobes. So if you move here, you can see that there are two types of approximation we are dealing with. One is the McDonald's approximation, and the second one is the Poissar's approximation. So it means that we are dealing with the another two types of approximation for omnidirectional pattern. Now, if we compare it with respect to n, you can see that for a high number of n's, both of these approximation have the similar behavior. Like the Poissar and McDonald's are very near to each other, but with the low number of n's, they are very, very similar to the, what you should say, exact approximation. Okay, the trend is the same for omnidirectional pattern, that for high number of n's, your beam width decreases. So I am going to solve one question for you. Okay. So this is example 2.7 I'm going to do. Are we good till now? Do we have any questions? So what we have done today is that we define that there are two types of patterns, radiation intensity. We can generalize our scenario based on directional pattern and omnidirectional pattern. For directional pattern, we have two approximations, Cross and Thai and Pereira. And for omnidirectional pattern, we have two approximations, McDonald's and Poissar's, right? So that's what we have done. And I want to solve one of the numerical for you. That's I'm going to do 1 minute. Okay. So this question is, okay, it says the radiation intensity of major lobe can be represented as okay, so what do you think? It's some omnidirectional pattern or like the directional pattern?
Directional.
Okay, Michael Bond, what do you think? Migo, what do you think?
Directional.
Okay, why? Why do you think it's a directional pattern and not omnidirectional? Aaron?
Because of the cosine n.
So for omnidirectional, what it should be?
Wouldn't it be sine?
Yes. Okay. So radiation intensity exists only. What should be the limits then of theta? If it is a directional pattern, what should be the limits of theta? Josh?
Would it be 0 to pi over 2?
Why?
Just because it's a directional
I cannot
pattern.
hear you. You're very, very low. What?
Is this better?
Yes.
Okay. I'm not entirely sure why. That's just the way I'm picturing it, the way it should be. I can't like explain it.
Yes, because if you're saying that if it's a directional pattern with one major lobe, then it should be above this plane. Okay? Yes, you're right, that it should be pi by 2. And your pi by 2 is, theta is from here to here, right? Josh, are you good? Do you
Yeah,
think
that
this
makes
is
sense.
fine?
Yeah.
Okay. So we need to find beam solid angle, exact and approximate, and maximum directivity, exact and approximate. They want us to compare with, I think, cross equation. Okay. So first, for the solution, we need to find the half power beam width. Okay. So how do you think we should find half power beam width? Because in the book, they just totally write it that your half power beam width is this. But we can find it, our half power beam width, from this. So what should we do to find our half power beam width?
Would you set cosine to the 4th power equal to 1/2 to find that angle?
What? Yes, I think you're right. What you're saying?
Would you set cosine to the 4th power equal to 1/2 and find that?
Yes. So our half power beam width is when your radiation intensity is 1/2. Okay. So that will become and if we ignore B naught, that's a constant value, then our half power beam width will be so I did it, it's coming as 32.765. If I do it in degrees. So that is your half power beam width. Not the beam width, it's the half power point, right? So for the beam width, so if this is your lobe and this is your half power point at 32.765, of course your beam width will be the double of that. So it means that your beam width is 32.765 into 2. So your half power beam width will be So I feel normally the question is not difficult. It's the formulation, like how you formulate the problem is the key. So if you know how to solve half power beam width, you're good. Okay, so now changing it into the radians, your half power beam width will be 1.1437 radians. Okay, and So they said that the two beam widths are equal. So the other beam width, we also take it as 1.1437 radians. So now what we have to do is we find beam solid angle exact and beam solid angle approximate. So beam solid angle exact. Okay, so we know that our exact beam solid angle is 0 to pi by 2 and 0 to 2 pi and sine theta d phi. Because this is the normalized scenario, that's why we are not adding b naught in it, and that will become yes, cos 4 theta sine theta d phi. Another thing I was thinking is that I think you guys know how to solve the integrals, but if there is a difficult integral that you need to solve, then I will maybe provide the like the integral table in which you can see that this integral comes as this integrals come as this. But if it is a simple integral, I mean, then you should be able to solve it. So pi by 2, they are all the time. Okay. So do you think this is a simple integral or this is a difficult one?
I think it might be a little long, but I think it's kind of straightforward if you break it apart, like, right?
So do you think that when I solve this integral, we see that if it has the derivative in it, right? So if cos 4 theta's derivative sine theta is there, then it should be simple. So then it should be right. What is the derivative of cos theta? Minus sine theta or sine theta? Chen, what do you think?
I'm
Am
pretty
I
sure it's
right?
minus sine theta.
Yes, then you should multiply the minus, okay? And I should not write it like this then. I should write it like this. Is it fine? Do you remember integrals? Yuri?
Yeah, sounds good.
Do you remember integrals? Do you think we should be having a table? I will give you the table, okay? Because I don't expect you guys to waste an extra energy on finding the integrals, okay? So
Yeah,
I will give the table, and I mean, it's long time, we can forget it, but if we know how to do it, it's fine, okay? So exact beam solid angle, we are done. So we will be doing approximate. It's a multiple of two solid angles, and it will give you 1.308 steradians. And if you solve the above one, I think, what is 2 pi by 5? Then we will know that whether it's near or not. What is 2 pi by 5?
1.256.
1.256. So it's near, but it's not, I mean, exact. Okay, so the B part is that we want to find exact directivity and approximate directivity. So for the exact directivity, if I use this, so which of the, so this is exact, which of the solid angle I should write here? 1.256 or 1.308? Ria?
1.256.
Right. So I will write 1.256 and yes. So whatever the answer will be, my directivity. So is it 10? I think so, because when you write it as it is, this comes as 10. Okay, so now approximate. Okay. So that's the scenario how you will find the exact and approximate things. Got it? Okay. Okay. Then one minute, I need to see whether this program is working. Okay, maybe next time I will show you the thing that I was talking about. Okay, so I think that's it for today. And we are now, you are able to solve some of the questions in the homework, but still I will talk about it on Thursday. I know by Thursday you will be able to, discuss homework in a more engaging way. Okay, so we will be doing this on Thursday. Other than that, next time we will start a new topic, and please fill the minute survey in, and we are good. Thank you.
Thank you.
Have a good one.
Thank
You
you.
too.
Good day.
Thank you. Have a good weekend.
Thank you. Have a nice day.